Welcome back to the third and hopefully last part about the basics of Hall effect angel sensors. In part 2, we had a squiz at the circuits here on my breadboard and on the breakout board, both very simple affairs, and we had an in-depth look on the Arduino code that makes the whole thing here tick. Complete code walkthrough, 15 minutes or so. This time we will have fun. We will have a look on the oscilloscope, what's actually happening on the SPI bus. And in the end I have come up with some more experiments I want to carry out here. Oh, dimming. With my Lego wheel with a magnet on it, and yeah, the Hall effect angle sensor. However, to really understand what's going on the PCI bus, you will have to watch the code walkthrough in part 2. Sorry about that. Otherwise, enjoy. Let's start with a single SPI transaction. The function in the code has incidentally the same name on the SPI bus. So the yellow trace on the top is my chip select signal, which goes, of course, low at the start of the transaction and high again at the end of the transaction. In between, in blue, we have the slave clock, 16 clock cycles, and clock idle high. We talked about that in part 2 also. The reddish trace here is actually my master out slave inline, which is completely zero, but that's actually a command. All 16-bit 0 is the command to read out the angle from the sensor. And green, of course, the trace, that's my slave out master in, slave out, where the angle is transmitted back. Note that the last bit changing here, that's just our parity bit, and then this is a 12-bit value in total, as we have seen in the code too, and only the last few bits are changing, the least significant bits. The most significant bits stay stable unless I turn the wheel, and then we get, of course, another value here, turning it again, and so on. But remember, the data returned here is not the data for that command here, but the data returned from the chip for the previous command, from the previous SPI transaction it received. So my whole read register function looks at the PCI bus like that. Remember, we don't cache or memorize what was the last command. So the read register in the software always sends a command, and then in a second SPI transaction it reads the returned data. So this is the returned data for this command here. Incidentally, I'm only sending here read angle register commands, 16 times 0. So yeah, there's room for optimization here, but I also talked about that in the code review walkthrough in the second part. Now I changed the time scale again, and we see that 2 SPI transaction here, and then a whole lot of time, really nothing happens. And we will, talk about that slope later on. That's a little artifact of how I built my circuit. Let's zoom in even more. According to my code, I have a transaction every 250 milliseconds. So 2 transactions, I wait for 250 milliseconds, another 2 transactions. So what happens if I remove the magnet and provoke errors? That's a whole lot more going on here now, but let's have first a look at the printed out error messages. Okay, let me first stop the auto scroll here. So the transaction actually starts here. That is one transaction block here, these 5 lines. It starts with me sending a command, or read register, and I get in the transmission back data errors. Yeah, these were these 2 bits that are included in each transmission from the chip back. And the only data error I get is a general error. Then I make a second, if I get an error, I make a second read register command, but this time I read the error register. Again, watch the code in part 2. And of course I get again back the general 2 error bits, one of them general error, the other one is not set, that would be low voltage warning. And I get the data for the error registers. And the only error I get is, of course, magnet lost. And then comes the next transaction. And that is only a single one. It will be only a single one, and that's me resetting the error register. Now, I know it's a little bit complicated, but let's have a look at the oscilloscope, what's going on. So the whole cycle starts with me reading a register, the angle register, sending the command, read register, and receiving the data back in the second transaction. Let's zoom in. So I'm sending here my 16 times 0 command. Yeah, that's my first transaction. I don't expect to get any data back, but in fact I do because of the previous commands, and that's the general error flag here. The first bit, the most significant bit in any transaction, any 16-bit word you get back from the chip. And then I try to read the data that comes back, the angle in the second SPI transaction. We are still, 2 transactions for the read register thing. And the error bit is still set, and I get some angle information, but I disregard that because, I have a general error warning. So we were just looking at the first 2 SPI transactions that basically do a read register. In this case, all 0, so read angle register. Now we have a look at these 2 SPI transactions, and you see I actually sent here a different command. Now I'm reading, since I know there is some error, the error register. And that is a very good example how the chip returns data for the last command received, because what's returned here is basically the angle register, because the last command I said was return me the angle register. But now I want the chip to return the error register, and that is lots of zeros, 1 and more zeros. Go to the software again to see the exact definition of that command word here. And in the next transaction here, I actually, and just because I'm lazy, I'm sending the same command again here. You have to send some command. Even all zeros are a command. Here it returns the content of the error register. And after that, there follows a 5th SPI transaction, this time only a read register. And yes, we will talk about these later on. So I read here in 2 transactions my angle, and I got an error bit set, so I read the error register to see exactly what's the problem. I printed that out on the serial monitor. And then I sent a command to reset to the config register to reset all the error flags. Why? Because some error flags need explicit resetting to get rid of them. Let's zoom into that thing. It's not very interesting. So that's the single SPI transaction to reset the error register, and this is obviously different command. Again, look at the software, which bits I have to set. Obviously, 2 bits here to address the register, and I think the last bit here, if that is set, that means reset the error registers. And what's returned here is still the error register, because that was the last command we sent. And if I return the magnet to its rightful place again, everything gets back to normal. And sorry, my notebook is in standby, but you would see here, well, yeah, we can do it. There it is. Okay, and it's hopefully everything is still working. Yeah, it is. Now, I also talked about that resetting these error flags, especially the low power error, and we didn't have a low power error, we just had, magnet lost error. Yeah, magnet lost, somebody pocketed it. Resetting, where was I? Yeah, resetting that power lost flag is most important, because otherwise the chip won't work properly. And how do I show you that? Yeah, I know. We capture the whole power up process. How about that? Okay, I hope I have my settings all right. Single capture, and let's power the... Oh, there was a spike. That was not good. Let's try that again. And there we are. Okay, let's zoom in. Okay, after power up, and we can zoom in even a little bit more, there is my first group. Yeah, we know that already. Yeah, complete zero command. Trying to read out the angle. And of course, I get the error flag here. That's this bit in the returned data. I also get an angle, but the error flag, general error flag, is set in that transmission. And therefore, further down the road, I do what we've already done before. I read out the error register. And then there's the last command. I reset the error register, specifically the low power error register. Let me see. Did I capture the next thing? No, I didn't capture the next regular operation, so just reading. I am capturing here on a much larger 20 millisecond timescale per division, and you see after startup, the error handling, the total 5 SPI transaction, and after I reset the flag, that error flag, that power down, low power warning flag, the next transaction here much smaller. Maybe we can zoom in. There we have our 2 regular SPI transaction then, and the error bit is no longer set. Nice, huh? Okay, that's it so far with what's going on the SPI bus the whole time. You might ask yourself, why so complicated? And the answer is, this chip here is actually an automotive part. So it has a lot of fail-safes built in, and when anything goes wrong, it first requires the controller to say, okay, tell me what's wrong, we can make it better, come on, reset everything, I trust you again, and so on. Because especially that chip here is, I mean, that's an obsolete chip. I told that in part 1, but similar chips and the successor, the what it is, the A1335 from Allegro, they are, for example, used to measure the position in your in your power steering in your car. And you want some, safety margins there. There are also versions of this chip, a little bit with more legs, more pins, with actually 2 redundant sensors inside. 2 redundant circular Hall elements. Again, watch part 1. To make that really safe. But there was something else I wanted to talk about. And that's these, it almost looks like a discharge curve of a capacitor. That one not so much, but especially that one here. And in fact, that's exactly what they are. Discharge curve of a capacitor. Please note when we zoom in here, we end the transaction on a high bit. So the bus is high, and then chip select goes off or goes high. And then our SPI chip, it goes on, because it's for bus, it goes into high impedance mode. So what we see here is the discharge of all the capacity we have in our transmission line. And you see that doesn't happen if the last bit in a transmission was actually low. I mean, transmission, again, master in, slave out, from the slave to the master. Then we have not this phenomenon, but if the last bit the slave transmitted was high, and afterwards everything goes high impedance on that master in, slave out line, you get these discharge curves. I mean, the master out, slave in pin on the controller on our Arduino is always high impedance. But maybe it's better we look at the drawing, huh? So, as I have mentioned, all lines but the MISO line, so the slave clock line, the master out, slave in line, the chip select lines, are all driven actively by the master all the time, either high or low. However, the master in, slave out line can be dangling in the breeze. So of course here on the master side it's an input, so it's high impedance. According to the 18 mega data sheet, we have a leakage current here of maximum 1 microamp. And when all the slaves have no chip select signal, so all the chip selects for the slaves are high, they of course also go into high impedance mode here. The output stages of the slaves look something like this, so 2 MOSFETs in a totem pole arrangement, and we can also assume if both MOSFETs are off that we get a leakage current here in the same order of magnitude, so about 1 microamp. So basically that whole line here, our master in, slave out line, if no slave is talking, is isolated. Now, if you consider that I'm running all my SPI lines, ground and 5 volt through this 50 centimeter flat flex cable from my breadboard to my breakout board, so all lines in parallel, we've built quite a capacitor. If we just consider the MISO line here, which is left dangling high at 5 volts at the end of our SPI cycle, that line has 4 parasitic capacitances to the other 4 lines. So we can draw that as the MISO line being coupled by 4 little capacitors with the other 4 lines. Now, two of these capacitors, and initially these are charged plus minus, are connected to lines that are 0 volts. Ground, of course, 0 volts, and master out, slave in also goes to 0 volt after our SPI transaction ends. The other two capacitors, again in red, are initially discharged. Yeah, we have 0 volts across them because they are coupled to lines that are at 5 volts. Chip select goes up to 5 volt and VCC is, of course, always at 5 volt. Now, as the the voltage decays away through the leakage currents in our connected chips on the master and slave outline, we of course discharge these capacitors here because they were initially charged. But we also have to charge up these capacitors here. They were initially, had no charge, were empty. But in our end state, so MISO completely decayed down to 0 volts, these capacitors have to be charged up. Green plus minus, because in the end we have here a plus 5 volt line connected to MISO down at 0 volts. So all these capacitors contribute to the effect that we have here, stray capacitance on the MISO line, which obviously can be a problem if your data lines get very long. It was just nice to show it here with that extreme example using a 50 centimeter flat flex cable. But I don't want to leave you on such a dry theoretical note. So, Oops, data error. Yeah, I'm stretching here the distance of axis. Remember part 1? My plastic sheet is going down between the magnet and the sensor. The reason being, I want to test something out with some more magnets. So yeah, we're almost here at 100 degrees. Okay, pretty much at 100 degrees readout here from the position. And the question is, if I have another sensor nearby, what's the crosstalk between the two magnets? So of course, if I put the magnet close to here, so you can still read it. So I try it from the back. You see how my readings get all over the place. No longer 100 degrees. However, if the magnet is sufficiently far away, let's try it behind here. So that's about 2 centimeters. Oh, we still get a little crosstalk here. Plus minus 2 degrees at the worst, or plus minus 1 degree. But if I go, a little bit further, let's say behind here, you see the crosstalk is really, really small. I mean, it's, between the normal noise you get here on the sensor, it's almost not noticeable. So crosstalk from other magnetic sources is really something, or changing magnetic sources to be exact, is really something you have to consider when doing, come on, can I get some crosstalk? 103 degrees, 104. If you design such a solution with a Hall effect angle sensor. I mean, they are obviously immune to anything non-magnetic you put between them, again, see in part 1. And they are also absolutely immune to dirt as long as it is non-magnetic. Yeah, iron filings would be a bad kind of dirt or iron dust, but anything else, yeah, it doesn't matter. And that's the really nice thing about these sensors. I think I've done everything I wanted to do today. There will be more videos in regards to these Hall effect rotary position sensors. Yeah, the details. However, the chip I wanted to do that with, the A1335, still, yeah, available, a successor to that A1334. It's currently on back order, date unknown at my distributor, DigiKey. So, yeah, we'll see. Maybe I buy another chip. I have something from AMS in mind that only has 8 pins, so a little bit easier to wire up on a breakout board. We'll see. Anyway, till next time, bye.